We did our project on the lunar phases. The lunar phases are a distinct set of phases the moon goes through every 29.53 days, from a new moon of black sky to a full moon of bright light. They were generally not discovered by anybody, as many people suggest, because anybody can look at the moon and study it. However, some scientists suggest that the phases were discovered by Galileo, the Italian physicist, mathematician, philosopher, and astronomer. Each phase of the moon has a specific and recognizable shape and comes at the same point in the moon cycle every time. The lunar phases go in this order: new moon, waxing crescent, first quarter, waxing gibbous, full moon, waning gibbous, last quarter, waxing crescent. So, you start out with the new moon, the black empty sky, then it increases in visibility into the middle of the cycle. Comes the full moon, then it decreases in visibility again, and becomes a new moon once again to restart the cycle. Start off with the new moon, the blackness, the nothing, it's not there, you can't see it, it's not visible. Next we have the waxing crescent, and we know it's waxing because waxing would mean it's increasing in visibility, so it's going up, progressing toward the full moon. So the crescent, obviously shaped like a crescent. I can't really form it, but you know what I mean. Next we have the first quarter where half the moon is visible. Half. Then we have the waxing gibbous where you can see 3/4 of the moon, followed by the full moon, which is what everyone likes to see. It's completely visible, it's bright, werewolves come out, we all love it. Next, we decrease in visibility. We go to the waning gibbous, which is the 3/4 of the moon visible again, except this time we're going down, which is why we use the term waning. Next, we have the third quarter, also called the last quarter by some people, followed by the waning crescent, which is just another crescent, but it's going down, so which means next we restart the cycle again with the full moon in 29.53 days.
For our data, we used a calendar to determine which day of the year the phases fell on. The first column shows the day of the year, the second column shows what the phase of the moon is, and the third column shows the date that the phase falls on. We used our data table to create our graph of the moon cycle. On the x-axis, we have the day of the year, and on the y-axis, we have the portion of the moon that is visible. For example, if the day of the year is the 4th, then 0% of the moon would be visible. This means that it is a new moon. At 0.5, it is a quarter moon, and at 1, it would be a full moon. And you can see that it is periodic. Our graph shows the first 100 days in the year 2011, but since this is a periodic function, it will continue on throughout the year and through the following years. We formed our equation using our graph of the moon cycle. Our equation is y equals 0.5 sine of 2 pi over 29.5 times x minus 24 pi over 29.5 plus 0.5, where x is the day of the year and y is the portion of the moon that is visible. We developed our equation using the standard equation for sine, which is y equals a sine of b times x minus h plus c, where a is the amplitude, b is the frequency, h is the phase shift found by dividing h by b, and c is the vertical shift. A, which is the amplitude, is found by subtracting the maximum value by the minimum value and dividing by 2. Our maximum value is 1 and our minimum value is 0. 1 minus 0 is 1. 1 divided by 2 is 0.5. Therefore, our amplitude is 0.5. B, which is the frequency, is found by dividing 2 pi by the period. Our period is 29.5 days, which is the number of days that it takes for the moon to complete one cycle. So 2 pi divided by 29.5 is our B value. H is found by multiplying the phase shift by B. We already have our B value, which is 2 pi over 29.5. To find the phase shift, we compare our graph to the graph of sine of x. Sine of x would intersect the x-axis at 0. Our graph, if you take away the vertical shift of 0.5, would intersect the x-axis at a value of 12. Therefore, our phase shift is 12. So our h value is 12 times 2 pi over 29.5. When you solve that, it's 24 pi over 29.5. Our c value is the vertical shift, so it's how much our graph is shifted up from the original graph of sine of x. Our graph is shifted up 0.5. When we substitute those values into our equation, we get y equals 0.5 sine of 2 pi over 29.5x minus 24 pi over 29.5 plus 0.5. Now we can use our equation to predict the future behavior of the moon cycle. For our first example, we can use the independent variable to solve for the dependent variable. For example, on day 345, what portion of the moon will be visible? If we substitute 345 in for x in our equation, we get y equals 0.5 times sine of 2 pi over 29.5 times 345 minus 24 pi over 29.5 plus 0.5. Using our calculator to solve for the middle part, we get y equals 0.5 times 0.9714 plus 0.5. Solving this out, we get that y equals 0.9857. This means that on day 345, which is December 10th, 0.9857% of the moon will be visible. This is equivalent to a full moon.
We can also use our equation to solve for the independent variable given the dependent variable. This means that by using a value representing the portion of the moon visible, the y value, we can determine on which days that portion will be visible, an x value. For example, if our y value is 1, a full moon, we can use our graph to predict the days on which a full moon will occur, such as here, here, and here. By knowing that the period of our phenomenon is 29.5 days, we can use this to predict whether full moons will occur in future years by adding 29.5k, where k is the number of cycles, to a day that we already know it occurs on. Example, if you take the 49th day of the year, that's February 18th, and add to 29.5 times 12, which is a full year's worth of cycles, you get 403. Then if you take 403 and subtract 365, we get 38. So we know that a full moon will occur on the 38th day of next year. Now I'm going to use this equation to solve for 3 instances of the phenomenon, which in this case is a full moon. So, if we take 29.5, the number of days in the cycle, multiply it by 2 cycles, we get 59. Then if we add the first full moon of the year, which would be 19 days in, we get 78. And as shown here, 78 is March 19th, which is a full moon. Next, 29.5, let's multiply it by, say, 4. Now let's add 78. We get 196. As shown here, 196 is a full moon, which is also July 15th. Lastly, if we take 29.5 multiplied by, say, 5, and now we add, let's go with 137, we get 284. And as shown here, 284 is in fact a full moon on October 11th. And to prove this, I will show the table for these days again. As you can see, March 19th, the 78th day, is a full moon, as well as July 15th, the 196th day, and 284, October. In our equation, we use the variable 29.5 for x to determine how long the moon takes to complete its cycle. Now, this could cause error because it was rounded from the actual number of 29.53 days, which is actually how long it takes. So, you could actually use this equation to predict within a few seconds, minutes, or hours of the exact time the moon is going to be at its phase. But after this, years from now, you could be a day or two off, but generally this equation can be used to determine how long or when a phase of the moon will occur.